So we're going to look at the Banach-Tarski paradox, which makes the claim that you can take a sphere, decompose it into parts, rotate them, and then reassemble the parts in such a way that you get two spheres just like the original, which is a very interesting idea because it goes completely against our intuition. Rotations are supposed to preserve volume, and so the idea that we could get two spheres tells us that some very interesting things must be going on here. So to get started, we're going to first take a look at a group called F2, and we're going to end up decomposing this group and rearranging it to make two of them, just like we're going to do later with the sphere. So this group has four generators, X, X inverse, V, and V inverse. It's an abelian group, and so when X and X inverse are operated together, we get the identity 1, and same with V. So the operations of this group is just concatenating words together, or characters together to form words. So one thing I want to point out is that if we have inverses next to each other in a word, if we have X, X inverse, and then the rest of this, these will actually cancel out and we just get V inverse X inverse. So we're only looking at words in their most simplified form. So here are a couple examples of words that we can see. And so we have infinitely many words with all kinds of different combinations, and we're going to go ahead and get started with the decomposition of it. Okay, so now we're going to break this the group down into these four pieces, and we can think of MX as being all of the words that start with an X. And same for all the other four generators. So MX would look something like this. So here we have all the words that have only X's in them, but also words that have other generators in it, so long as it starts with an X, and we don't have inverses next to each other, because they're all completely simplified. Okay, so to reconstruct it, we're going to start using MX first. Let's take that piece. So that one's being used now. And we're going to multiply it on the left by X inverse. So what ends up happening is the beginning of all of these words now has X inverse. And so because it starts with an X, they're all going to cancel out. And so what happens after all of these cancellations is we're left with the following. And you'll notice that not only do we still have all of the X words, but we also have the V words and the V inverse words. So we've taken MX, and after multiplying on the left by X inverse, it becomes MX along with MV and MV inverse. So that's almost all of F2. So if we take this new modified MX and we add on, we take the union with MX inverse, we get all of F2. So because we're using MX inverse here, we can also cross that one out. That one's been used. So we can repeat the same process, beginning with MV, and we'll end up multiplying on the left by V inverse. And we get a similar situation where MV now becomes MV, but also MX and MX inverse. So we use MV, and we also tack on MV inverse to get a second copy of F2. Okay, now we'll explore something called Hilbert's Hotel. Imagine we have a hotel with a countably infinite number of hotel rooms that each holds exactly one resident. And then all of a sudden, a new person shows up. Well, if we want to accommodate them in the hotel, we can just put them into the first room. As for the person who's in the first room, they can go to the second person can go to the third, and so on and so forth. And we can continue with this process because for any room that someone is in, they can just jump to the next room, and there's always a next room because we have infinitely many rooms. So it's a really interesting idea. And it's important to remember that this also works if the person in the first room leaves. Everyone can just slide down a room, and so the hotel is always full. Now we're going to take this concept and apply it to a unit circle. So let's say that we have a point missing from this unit circle. And let's just say that that point is 1, 0. So this point P right here. We're going to show that it's possible to get this point back to fill this missing spot by filling in from infinity. So let's just have our radius from the center to that missing spot. And let's define rho to be a counterclockwise rotation for this radius of arc cosine of 1/3. So applying it once will move our radius to here. And so we can just continue to apply this. So here we'll have 2 of those. And as you can see, this is applying rho twice. So we can continue to do this infinitely many times, and no matter how many times we keep rotating around, none of the radii will overlap with each other. So right here we have an example, you can see it gets a little messy, of 50 or 45 or so radii all coming around. And we can have billions, we can have trillions of them, they will never overlap. And that has to do with the fact that the irrational number arc cosine of 1/3 doesn't divide to 2 pi, and we're able to just continuously do this. Now, we only have a countably infinite number of radii in this unit circle, and there's an uncountably infinite number of points around the circumference of the circle, because we're dealing with a real number of points. Though what we're actually going to do with this in order to fill the hole is define rho inverse. And the way this will work is it rotates by the same angle in the clockwise direction, like so. And what ends up happening is there's a point missing at 1, 0, but when we rotate, the point from rho prime will come back and fill that spot, and everywhere else, the point that was missing at rho prime will come from the previous point, and so on and so forth, just like in Hilbert's hotel. So everything just kind of shifts over by 1, and we're able to refill that missing spot in the circle. So it's time to use these ideas to duplicate a unit sphere. Now, here we have a point on a sphere of radius 1, and this radius that goes to the center, if we were to take this point and radius out of it, we'd be taking a little slim piece out of the sphere. So we're going to break the sphere down into parts, and the way we're going to do that is by taking a collection of points and the radii that go along with them, and putting them all into a set and just letting that be a piece of the sphere. So if we name all of the points and put them all into sets, then the points along with their associated radii will comprise the entire sphere along with the center point as well. Okay, so let's just start naming points. Let's take this one right here and just imagine a mutually orthogonal set of axes here. And so we can just kind of imagine the x-axis as going right through this point. And so we're looking at horizontal y and vertical z-axis here, and we're going to define 2 rotations. One of them is going to be along the y-axis, which will make the ball appear to be rolling like so. And then another one will be about the z-axis, which will make the ball spin, kind of like a globe. So these are the 2 rotations that we're going to define, and they're going to help us name the points. So I just want to make one brief callback to our group F2. These rotations, you could, they form a rotation group called SO3, and SO3 is actually isomorphic to F2, And so you could think of rotations like this as being like X from that group, and this could be like X inverse. And then rotating this way could be like V, and then rotating like so could be like V inverse. So we did a paradoxical decomposition with F2, and now doing it with SO3, we're going to see that it's possible here too. So let's begin by rotating in this direction by an angle of arc cosine of 1/3, just like we did with the unit circle. And we end up in this point which is right of our starting point. So we can call it R. Now looking from above like this, we can rotate once to get here, call it R. We can rotate again by the same angle from here and call that new point RR, and then 3 R's and then 4 R's and so on and so forth, going around and around countably infinite number of times, and we can get a whole bunch of points named that way. We can also do this similarly going left, and we can name this point here L, and then go on and get all of our L's. And we can do this without any of these radii overlapping due to the nature of our angle. And so we can get all of those points along with the points that we get from rotating upwards and downwards. We can get the point up here and call it U, and then UU, and so on and so forth. And so not just those points, we can also rotate up once and then rotate to the left another time and get the point UL, and so on and so forth, and go about this by getting a whole bunch of points named. As it turns out, this still won't be able to cover the entire unit sphere's surface, because just like our points from before were countably infinite, they couldn't cover the uncountable number of points on the circumference of the unit circle. It's the same situation here. We can't cover the uncountable number of points on the surface of a sphere. Fortunately, there's a way of getting around this. Let's just take a look at what we have so far. So we have a whole bunch of points named, all our U's, D's, L's, and so on. And we have all these crazy names, and this is just a very large amount of points. But a lot like F2, we need to keep in mind that we can't have inverses next to each other. So no up downs, no down ups, left rights, or right lefts. Like if we go up, up, down, and then up again, that's like going up twice. So we get these kinds of cancellations here. So just like F2, only the most simplified versions here, so that all of our points have unique names. And so everything is coming from our starting point. So our starting point is also one of our named points, but there is one issue that we run into in keeping the names unique, and these are the poles. So if we take a look at our sphere, and we have rotations going about the y and z axes. So if we go to the y-axis here, and let's say we're talking about the point that's right where the y-axis hits the surface of the sphere. From here, if we rotate about the y-axis, we're going to do rotations, but the point's not going to go anywhere because it's right here where the axis, it's on the axis that's being rotated. So we could keep rotating, rotating, rotating. They're going to all be talking about the same point. So it kind of throws a wrench in our naming convention here. So we're going to take the 4 poles where this happens and consider them separately. So that's here where the y-axis and 2 points hits the surface of the sphere, and also in the 2 points of the z-axis. We don't have to worry about the x-axis only because we're not doing any rotations about it. So we're considering our pole points separately, and now this is everything that we get from our rotations coming from our starting point. But we have an uncountable number of points to reach, so we're reaching a lot of points here, but it's not enough. So the way we get the rest of them is we start by considering any of the points we haven't hit yet. There are many. So we just take any of them, and from that point we haven't touched, we consider that to be a brand new starting point. And we run this entire process again, do all of these rotations, get all of these names with a new starting point, new poles and everything, and we get a whole new set of names, and we call all the names we get from one starting point, we call that an orbit. So you have the starting point and everything you can get from it. And so we keep doing that, picking a point we haven't reached and branching out from there to get all the other points. And we do that an uncountably infinite number of times. So the amount of points we're reaching is absolutely huge. And so only when we start counting in terms of uncountable infinity can we really reach all of the points. So here we have an uncountable number of orbits. So that's a lot of pieces. It's a lot of sets to work with. So we have to kind of organize it a little bit. And the way we do that is with the help of the axiom of choice. So we're going to take all of these sets, all of these many, many orbits, and organize them. So we'll create a set, we'll call it L, and it'll be the set of all the names that have an L in the leftmost part of the word. So down here as well, but none of these, because this has a U, this has an R, and this has a D, and we organize it that way. So because of the axiom of choice, we can grab all the L's, all the words that have an L in the leftmost part of the name from all of the other sets and put them into the set L. And so we do the same thing with R, U, and D, and we also create two other sets, one with the starting points and another one with our poles. So we can collect all of the points on the surface of the sphere and put them into these sets. And then we also want to remember that along with all of these points on the surface and the radii that connect to the center, we also have the center point, just as a lone point, not a set. And with these pieces, we will reconstruct two spheres. Now, to make a unit ball, we need all of these 6 pieces plus the center. So I have them listed out here, and every time we use one, I'm going to cross it off. So let's just begin by using the left piece, and we can consider that one used of our 6 pieces we have to work with. So again, here's the left piece. It has all of the words that essentially begin with the letter L. So what we're going to do is rotate this piece to the right. And by rotating it to the right, we add an R to the front of every single one of these words. Now, after cancellations, what will happen is we get all of the left words, we get all of the downs and the ups, but I want to draw a lot of attention to this right here, because what this means is that we get the starting point. Because if you look back and you have our starting point at X, if I can find it, and we had from all of the different orbits where it went to the left, if we're taking all of those and rotating them back to the right, we're getting all of the starting points from all of the orbits. So we're taking the left piece and turning it into so much more. So just using the left piece, it turns out that we get the left, down, up, and the starting points. So we're missing a little bit more, but we have a lot of pieces to work with. So we can add them to our first reconstruction. So we can throw in the right points, and we can also throw in the center and the poles. So if we put those 3 pieces into our first reconstruction, we get the right points, we get the poles, and we also get the center. And with that, we have the entire sphere recreated, and we still have these pieces left over, which we can use to make the second one. Okay, before getting into our second reconstruction, I just want to briefly mention that because all of these points have unique names, all of these sets are disjoint. So these are disjoint unions. Okay, so getting back into it, we can go ahead and start using our up piece. So we're going to cross it out because it's now being used in our construction. And again, these are a lot of names that, some examples of names that you have in the set of names. So here we're going to rotate all of them downwards, and as a result, we get all of these cancellations as before, but we run into an issue, and it has to do with the fact that we're getting the starting points again. So we have our up pieces, our left piece, and our right piece, but we're also getting the starting pieces, which is okay, except for the fact that we already have starting points. So we want to reconstruct the sphere without anything left over. So we don't want to get starting points out of this. One thing that we could do is take everything that is an up piece and pull it out before the rotation and just not rotate those. That's one option if we were to do that. So this rotation just wouldn't happen. We're putting our ups out here. But then when this rotation happens, we have the ups that we pulled out, but we also get these ups here. So what we end up doing here is pulling out not just the ups, but anything that is just a string of views. We have to take all of those out, rotate everything, and then put the string of views back in, and that way we don't have any extra copies of anything we don't want to duplicate. And so from this, we're able to get the up pieces, the left pieces, the right pieces, and not the starting points. So what we're going to do now is add the starting points and the down pieces to our union here. So we get the starting points and we get the down pieces, and all we're missing are poles and a center. But we're out of pieces. Fortunately, that's not an issue. So check out this sphere right here, and just imagine that from the center we have a circle within the sphere. So a circle with one point of it missing, we already know that we can fill in from infinity. It's like looking at Hilbert's Hotel or the circle trick that we did before. So through that, we can get our center. As for the poles, any place that we're missing a pole, that we have a pole hole, there's a circle that goes around the sphere that doesn't intersect with any other circle, any other pole hole circle. So what we can do for this infinite number of pole holes is fill them in from infinity in the same way. So through that, we get our poles and we get the center, which completes the reconstruction of the second sphere. So the Banach-Tarski paradox really is a fun idea. There are a couple of solutions, one of which is to just not accept the axiom of choice. That's one thing that you could do. But as I understand it, whoa, we're not supposed to get 3. As I understand it, it's something that nowadays is pretty reasonably accepted by mathematicians, and so it's not really an issue. A solution that I think is a little more interesting is to get into measure theory and consider the notion of non-measurable sets. And when you think of things not having a measure, we can't give things a measure, it makes a little more sense that something like this could be possible. So that's the Banach-Tarski paradox, and from one sphere we can get 2.